Hi everyone! Today we're looking at one of the most exciting breakthroughs in modern artificial intelligence, diffusion models. If you've ever used tools like Midjourney or DALL-E to generate mind-blowing artwork from just a text prompt, you've seen these models in action. Let's break down how they work. First, we'll look at the core concept of what diffusion actually means. Second, we'll look at the mathematics and neural network architecture powering it. Third, we'll look at how these models are trained, and finally, we'll talk about the real-world applications changing the tech landscape today. Let's start with Chapter 1. What are they? Normally, we think of a sculptor starting with a block of marble and chipping away to reveal a statue. Diffusion models do the exact opposite. Think of it like starting with a pile of dust and learn how to assemble that dust step by step into a masterpiece. Instead of trying to create an image perfectly out of thin air, AI's core trick is learning how to undo noise. By mastering how to clean up an image, it learns what the real world actually looks like. To make this happen, there are two phases: the forward process and the reverse process. The forward process is simple and mechanical. We take a perfectly clear image and gradually add random Gaussian noise to cover over hundreds of steps. Each step only depends on the one right before it, which is a concept known as the Markov property. Eventually, the image is completely destroyed, leaving us with pure static. The next step is the reverse process, or denoising. This is where a neural network steps in. Its job is to look at the static, predict exactly how much noise was added, and remove it. Once trained, we can hand it any random static, and it will iteratively clean up until a brand new image emerges. Now that we have the concept down, let's take a look at Chapter 2, how they work mathematically and structurally. In the forward step, we use a formula where alpha controls the noise schedule, dictating how much static we inject at any given moment. Our training objective is to simply minimize mean squared error. In plain English, we want the difference between the actual noise we added and the noise the AI guessed to be as close to zero as possible. Why do we do this? Because predicting noise is a structured, mathematically stable problem. The AI doesn't have to guess a whole image at once. Instead, it just makes tiny stable corrections until a coherent image appears. What kind of neural network is actually doing this? It's called the UNet. It takes a noisy image and current timestamp as inputs. First, the encoder compresses the image through convolutional blocks down to a tight latent representation to understand the high-level context. Then the decoder upsamples it back to full resolution. The dashed lines are skip connections. They allow the network to pass fine-grained spatial details directly from the encoder over to the decoder. This ensures the final noise prediction is very precise, and allows us to subtract it and get a beautifully crisp result. This brings us to Chapter 3. How do we take everything we've discussed and train a model from scratch to achieve denoising? The training pipeline is a loop. First, we sample a real image from our dataset. Second, we pick a completely random time step, t. Third, we add noise to that image based on our schedule. Fourth, we feed that noisy image into our UNet and ask it to predict the noise. Fifth, we calculate the loss by comparing its guess to the real noise we injected. Finally, we backpropagate that error to update the network's weights and do it all over again. Now, once the model is fully trained, how do we use it to create something new? This is called the sampling process. We start with absolute randomness, pure Gaussian noise. We feed that noise into our trained UNet. The model looks at it, predicts the noise pattern, and subtracts a tiny bit of it, giving us a slightly cleaner version. We repeat this over and over. Historically, this took up 10,000 slow steps. But modern techniques like DDIM use clever math shortcuts to get the exact same high quality results in 20 to 50 steps, making real time AI generation very fast and practical. Let's look at the real world landscape and the massive models that are shaping creative AI today in Chapter 4. It all started in 2020 with DDPM, the foundational paper that proved diffusion can match the image quality of older AI methods. Then came Stable Diffusion in 2022, which changed the game by running in a compressed, latent space rather than calculating every single pixel. This meant they could finally run on consumer graphic cards at home, and being open source, it exploded in popularity. In 2023, OpenAI natively integrated DALL-E 3 into ChatGPT, making image generation as simple as having a normal conversation. As you can see from the global search interest chart, Midjourney completely dominates public interest. Diffusion isn't just for pretty pictures anymore. The universal principle of sculpting structure out of chaos is expanding into new frontiers. We are seeing it power hyper-realistic video generation with OpenAI Sora and Runway, 3D object generation for video games, and clean audio synthesis. Even in medicine, scientists are using diffusion models for protein structure prediction and molecular design to discover life-saving drugs. Here are the key takeaways. First, diffusion models create data by reversing noise, making their trading very stable. Second, this field has evolved very fast from DDPM to stable diffusion in DALI. Third, this exact same denoising concept is now transforming other fields. Thank you so much for exploring diffusion models with me today.